Hello students, Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will discuss regenerative or Hopkinson's test, which is performed on DC machines. And this test is also called back-to-back test. In this test, one motor and one generator are coupled with each other, as you can see in this figure. This is the motor, and this motor is supplied by the electrical power by means of this DC voltage supply. Here we have an ampere meter, and this ampere meter A2 will measure the input current, right, which is I2, and this is a shunt wound DC motor, and this is a shunt wound DC generator. We have another ampere meter A4 over here, which is used to measure the field current of this motor, and we have a variable resistor R2 over here, and the purpose of this variable resistor is to vary the field excitation of this motor, and by varying this field excitation we can vary the speed of this DC motor. This is the generator section. Here again we have this variable resistance in series with the field winding of this generator. Again, this is used to vary the field excitation, and by varying the field excitation we can vary the flux and induced EMF of this generator. This is the ampere meter A3, and it will calculate or it will measure the field current of this generator. This is A1 ampere meter, and this is used to measure output current of this generator. So output current of this generator is I1, and this generator is coupled with this motor. First of all, we will turn on this DC supply, and we will vary the field excitation to adjust the speed. After that, this generator will start running, and then we will vary the field excitation of this generator to equate the output voltage of this generator with the input voltage of this DC supply, right? So this is the output current of the generator, and here we have used a switch and a voltmeter V1. So by varying this field excitation, its voltage will vary, and we will do this changing until this voltmeter reads zero. As soon as this voltmeter reads zero, it means the voltage at this side and this side are equal. So after that, we will remove this voltmeter and turn on this switch or close this switch. So at that instant, the motor will be running the generator, and the generator output will be fed to the motor, and most of the powers uh, between motor and generator will be shared with each other, right? Only minute power will be taken from this input DC supply, and that minute power will be equal to the losses taking place across this motor generator set. So motor M is run first by main supply with switch S open, right? This is the switch S. As a result, generator G starts showing some voltage. Okay. Speed of M is adjusted by R2. Then R1 is adjusted to equate the generator voltage with main supply such that V1 reads 0. Then switch S is closed. At this point, most of motor input is supplied by the generator, and all input of the generator is supplied by the motor. So at that instant, motor input will be equal to V into I1 plus I2, right? The total motor current will be equal to I2 current from the supply, and I1 is the current from the generator, and the voltage across the meter is V. So total input power taken by the motor will be equal to V multiplied by I1 plus I2. Similarly, total output power of the generator is equal to V times I1. The generator output voltage is V, and the generator output current is I1. Now, assuming both machines have same efficiency, the output power of the motor is equal to efficiency times input, and this is efficiency and this is motor input. Similarly, output power of the generator is equal to efficiency times input power of the generator, and input power of the generator is equal to output power of the motor, because this generator is solely run by this motor. So generator output is equal to efficiency times generator input, and generator input is exactly equal to the motor output. So generator output power is equal to efficiency times motor output, and that will be equal to eta multiplied by eta V into I1 plus I2. So that will be equal to eta square V into I1 plus I2. So this is the case when both machines have same efficiency, and from equations 1 and 2, this is equation 1 which is showing us generator output. This equation 2 is also showing us generator output. So we can equate equations 1 and 2 and we will get this expression. So from this expression, the formula for the efficiency eta can be written as square root of I1 divided by I1 plus I2. If efficiencies of both machines are different, then we have to do some other calculations. And suppose Ra is the armature resistance, and I3 and I4 are the excitation currents of the generator and motor respectively. And you can also check this in this circuit diagram. I3 is the excitation current of the generator. I4 is the excitation current of the motor. So we can calculate the copper losses across both the motor and the generator. Armature copper loss in the generator is equal to I1 plus I3 square Ra, and armature copper loss in the motor is equal to I1 plus I2 minus I4 square multiplied by Ra. So these expressions can be checked in this circuit diagram. Armature copper loss in the generator is equal to armature current square multiplied by armature resistance. Armature current of the generator is equal to I1 plus I3, right? So this is I1, this is I3. Similarly, armature current of the motor is equal to I1 plus I2 minus I4, right? So I1 plus I2 minus I4 square multiplied by Ra is the armature copper loss across the motor. Similarly, shunt copper loss or the field copper loss across the generator and the motor can be calculated by this expression. And shunt copper loss or field copper loss in the generator is equal to I3 square RF. Now RF is the total resistance of this rheostat and this field winding. But we don't know the actual resistance which we have adjusted of this rheostat. So it is difficult to apply this expression, right? I3 square RF. But we can use alternative expression which is V into I3, right? Vi is also an expression of the power loss. Voltage across the generator is V, and the current in this branch is equal to I3. So the shunt copper loss or field copper loss across the generator is V times I3. Similarly, shunt copper loss or field copper loss across the motor is V times I4. So we have evaluated the expressions for armature copper loss and shunt or field copper loss across both the generator and the motor. Now the power drawn from the supply is equal to V into I2, and that power is actually equal to the total losses in the generator and motor. The reason is that this motor is running this generator, and this generator is running this motor, right? So if both these machines were lossless or ideal, then there would be no losses and the system would go on running, right, ever, because all the mechanical power generated by the motor would be delivered to the generator, and all the electrical power generated by this generator would be sufficient to run the motor. But since there are some losses, so the input drawn by the motor is not exactly equal to the output of this motor. Similarly, the input of this generator won't be exactly equal to the output of the motor, because practically the efficiencies of both these machines are less than 100%. So in this case, some power will be drawn from this input voltage supply, and that power would be exactly equal to the total losses across this motor and the generator set. So in this case, Vi2 is the total loss in the generator and the motor, and we can calculate the total stray losses, and those stray losses will be equal to the total losses, which are Vi2 minus all the copper losses across the armature winding and the copper losses across the field windings. So by mistake, I have missed a bracket over here. So I have used a bracket over here, which is a closing bracket, but there must be an opening bracket over here. So you should put that opening bracket over here so that we can say that all the stray losses are equal to the total losses minus all the copper losses. So stray loss per machine are equal to W by 2. So this is equal to W, and per machine stray losses are equal to W by 2. Now for generator, total losses are equal to the armature copper loss across the generator plus total field copper loss across the generator plus stray losses divided by 2, right? So in this case, P out is equal to V multiplied by I1. This is the output power of the generator. So efficiency will be equal to output over input. So this is output and input is equal to output plus losses. So this is our efficiency expression for the generator. And for the motor, total losses are equal to the total armature copper loss across the motor plus total field copper loss across the motor plus W by 2, right? So W by 2 is the stray loss per machine, and that is equal to Wm, total losses across the motor. Now the input power is equal to this V multiplied by I1 plus I2. This is the input power of the motor, and this is the same expression which we have also written over here, right? So motor input is equal to V times I1 plus I2. Now the efficiency of the motor is equal to output over input. This is input and output is equal to input minus losses. So this is the efficiency expression of the motor. Now the advantages of Hopkinson's test or back-to-back test are power required is small as compared to full load powers of each machine. This is the first advantage because the only power which is drawn from the supply is equivalent to the total losses across both the machines, right? The actual powers or bulk powers which are consumed by both the machines are provided by the other machine. The input power drawn by the motor is given by the generator, and the input power, most of the input power drawn by the generator is given by the motor. Only this input supply is sufficient to overcome the losses across both the machines. So this is the first advantage. And the second advantage of this Hopkinson's test is that due to full load conditions, any change in iron losses due to flux distortion can be observed. So this test also incorporates the effect of armature reaction because both the machines are running at full load conditions. So if there is armature reaction, there will be a flux distortion, and whenever there is a flux distortion, the iron losses will change. So that change in iron losses will also be considered or will also be incorporated in this test. So among all other tests which are performed on DC machines, this Hopkinson's test or back-to-back test is the most expedient test, and it gives the best performance and accurate efficiencies at full loaded conditions, and it includes all the effects of armature reaction, full loaded conditions, uh, etc. So that is all about our today's lecture on Hopkinson's test. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.